Welcome back. Let's talk about this logical equivalence implementation. What I'd like you to do is write a program in C to test expressions for logical equivalence. And this assignment is also about the difference between expressions and functions. So let's just go through this stuff. And first of all, you should have watched the previous video on logic and leading up to logical equivalence. I'm assuming that you've already watched that video. All right, so first thing you're going to have to do is implement these logical operations as functions. So I want you to implement functions A through H here. That is, to be totally clear about it, I want you to write a function called implication that takes two Boolean arguments, A and B, and then returns a Boolean argument. And if your compiler doesn't support Boolean as a data type directly, you can just use integers. So in C and C++, 0 is false, and any non-zero value is considered true. A lot of times, -1 is used for true when a particular function needs to explicitly assign truth to something. It'll use -1. But you can use any non-zero value. So to make it easier, we can just use 0 and 1. So 0 will be false, and then 1 will be true. But keep in mind that many times in C, the value -1 is used to indicate truth when you in certain situations. Anyway, write these functions here as functions. Now, some of these functions are already supported by the language as expressions. For example, and, or, XOR, and not. Those last four, you can actually write expressions that implement those operations. This is a bitwise and in C. You'd probably want to use the the logical and, which is 2 ampersands. And here, once again, here I'm using bitwise, which I'm just trying to express the operation, not so much the language-specific difference between bitwise and logical and. So don't get confused about that. All right, but anyway, there's the and operation, the or operation, and the exclusive or operation, and the not operation are already supported by the language directly. Once again, you should probably use ampersand, ampersand, and then bar, bar for logical and versus bitwise and. But I want you to write these functions here. I want you to write and as a function, or as a function, XOR as a function, not as a function. Now, of course, inside that function, you can implement and any way you want. And the easiest way to do that would be to, use ampersand, ampersand for and. But there's other ways. You could use a lookup table. There's different ways. All right, so these four are supported by the language, but still I want you to write these functions. Now these top four are not supported by the language. So implication, which we've talked about earlier, we use this mathematical symbol to express it as an expression, right? And here's bicondition expressed as an expression. Right, those two operations are not supported by the C language, so you would have to write a function. I mean, in C++ you could use operator overloading for like what is this? This is the pointer dereferencing up arrow, right? This one here, there's no operator in C++ that you could overload to produce bicondition. Here, I think there is a question mark operator. It's the trinary operator for if in C. That's a trinary operator, though. But it's not worth doing that. Although, in theory, if there are symbols available, you might be able to do it. But there aren't always symbols available to do that. But that's not what I'm asking you to do. I'm just bringing that up kind of as a discussion between C++ object-oriented features and C procedural features, which is not really the main crux to this assignment. Anyway, backing up a little bit, I want you to implement implication by condition. as functions, and then inside there, you're going to have to use some combination of logic to get that to work, some combination of if-else statements to get that to work. Or you could use a switch is another way to do it. You could also use a lookup table. Okay, there's a couple ways to implement these guys, and I'll leave that up to you. All right, now just to make a little more point about logic, I've given you two more functions, one called maybe and one called because. And these are two more logical operations that I've just made up, okay? And if you were going to write an expression, I've chosen the question mark to indicate maybe. And if theoretically speaking, if it were possible, which it isn't, but if it were possible to write an expression using the because operator, I've chosen the @ symbol to represent the because operator. So what I'm really trying to do is I'm trying to point out the difference between function notation, which is this kind of thing in this first column, and then expression notation, which is this kind of thing in this column. In the class, and this semester we've been talking about expressions with operators and operands a little bit, and then we were talking about functions, and those two things are two sides of the same coin, so to speak, or they're similar conceptually, but they differ just in syntax, right? So that's part of what this assignment is about. All right. So you guys know what AND is, you know what OR is, you know what XOR is. Those are just the regular truth tables we have for those guys, and you know what NOT is. Implication is in the text as far as its truth table, and bicondition is in the text. Now maybe and because I just made those guys up, and so I've given you the truth table here for maybe using the question mark, and the truth table for because. So I've just made up this output column. It's just a made up logical operation. The point being that in classical philosophy, implication has a particular meaning, and so does bicondition. Implication turns out to be useful, very useful, but it can be kind of vague in the language sense, in the natural language sense, although it's very useful in the mathematical sense. Likewise with bicondition, it's useful in the mathematical sense, but human language-wise, it starts to get kind of vague, as language can be ambiguous. Anyway, I'm just trying to make that point, how some logical operations are very clear, others start to get less clear. And then, but what about because and maybe? People say that all the time. It's just to make the point of about how human natural language and what people say in their verbal arguments is not particularly crystal clear logic-wise. And this is just to kind of drive that point home. All right? So I just made up maybe and because. So write these functions, get them to work, and then implement additional code to test expressions for logical equivalence. Like here I have P or Q. So I'm using the mathematical expression for or, P bar Q. Now once again, in the C implementation, 1 bar means bitwise OR, and 2 bars means logical OR. But we're just talking about mathematical OR here, all right? We're just P or Q, or P and Q are true values, and we're just doing a logical OR, textbook speaking wise. Okay, and then there's this other expression here, not quantity, not P and not Q. Are these two expressions the right-hand side? This thing, is that equivalent to the left-hand side here? I want you to write a program that does that for all of these guys, for all of these expressions, left-hand side and right-hand side. So I've given you some rules of precedence. We already know that not has highest precedence, and then and has this next in precedence, and then or has the next in precedence. So I've given you the precedence here of implication, that would be next, and then bicondition would be next, and then maybe, and then because. So when you're not given explicit parentheses around things to indicate precedence, then use these rules of precedence here. Okay, so after you get these functions written and tested and working, then in main, write these expressions as your input, so you can hard code the input, so you don't have to type it in at runtime. Just hard code the input and test it. And I've kind of done this for you already for number 3 here. Which one is this? Implication. This is for E. I'm doing E here. I'm doing the left-hand side of expression E. So I'm doing this thing right here, right? Which is not quantity P implies quantity Q and R. So you got to do the Q and R first. So that's this, right? So this thing up here, this is expression notation, or textbook logical expressions notation. Not necessarily C notation, but textbook logical expression notation, right? But in function notation, that would look like this. So the Q, you do the Q first, then we need to do P implies the result of this, so we do implication, and then P is one argument, and then the other argument to the implication function is this return value from the AND call, right? And then lastly, we not the whole thing. Okay, so this is an example of converting an expression notation to a function notation. Now this is important because there are a family of languages called functional languages, where all the code is all just nothing but a bunch of function looking things. So later on you might be exposed to that. Typically, I had to take that in my first semester of graduate school. You had to take a class on just functional. Well, it wasn't just functional programming. It was all the logic families, and one of the logic families we studied was functional programming. Anyway, so take the left-hand side and put it in this, and then do the same thing for the right-hand side. Put the right-hand side of this expression in this function notation, and then generate all the values of P, Q, and R for both of these guys, and check that their result is the same for every value of P, Q, and R, right? So you need to generate all the permutations of P, Q, and R, and I've given you a little hint on how you could do that with simple counting, but you could also use loops, which is what most students are most comfortable with. So here's the thing that I've given you to do that first guy. I've given you some code. So generate the left-hand side in terms of function notation, generate the right-hand side in terms of function notation, and then I've gone into a loop where I'm just generating true and false values, 0 and up to 1. I'm just counting 0 to 1, 0 to 1, 0 to 1 on P, Q, and R, right? 0 to 1. And so I'm generating all the true-false combinations for 0 and 1. There's going to be 7 of them. Or you could just count to 7, which is what I'm doing over here. But anyway, you could also use 3 loops if you want. And generate the resulting value of the compound proposition, right? The compound proposition big P1 for a particular value of P, Q, and R, and then the compound proposition P2 for those same particular values of P, Q, and R. Compare if they're true. Compare if they're the same. And if they're not, then they're not equivalent. At this point, you could break out of the loop because you only need one PQR value that they're false for. There's no reason to check the rest of these, but I do want you to generate tables of all the values. Yeah, so you don't want to break out of the loop here. You just want to set this false flag. So anyway, at the end of this loop, generating all the possible permutations of P, Q, and R, you just check if your flag, this equivalent flag, has been set for any of those values, and print out that things are, the two expressions are logically equivalent or not. So this is what the output would be. Of course, you got to do a format statement to do the title of the table. But then as you're generating all your PQ, well, here we're only doing P and Q, but some of them need PQ and R. The next one down here needs PQ and R. But anyway, just print print the table, right? P, Q, and R, print the whole table, and you can see by looking at the columns here, 0, 1, 1, 1 for P or Q, and then 0, 1, 1, 1, the same columns. So the compound propositions, which is this whole column and this whole column, are the same for all values of the little propositions P and Q. So these guys are logically equivalent, right? And then another example here, these two guys turn out to be not logically equivalent because these two columns are different, right? Here I have 0, they're different. The two columns here are different. They don't have the same values for all the values of P, Q, and R. So these guys are not logically equivalent. Right? So I've done one expression of these 8. How many is this? 6 of these 6 expressions. Just do the rest. Just duplicate this chunk of code here, 5 more times for all of these expressions, and generate 6 tables down in here. That's it. It's pretty easy program, really, I think, and it's good because it's nice to have a little program like this. I mean, you're not going to use in real life. You're not going to use maybe and because, and you're not going to use implication and by condition. But I'm sure all of you guys have written you've written logical expressions, and you'll maybe. I remember lots of times where I've been sitting down writing code, and I write a logical expression, and then I kind of scratch my head for a bit, and I think, and I write it again, and it seems like it's also, the correct. Like I've come up with multiple expressions that seem both correct, and they could have been logically equivalent. So it's nice to just, if you find yourself in that if you find yourself in that situation, you can just throw those expressions into this little program and actually generate the tables and see if they are the same. Okay, just a little way to check your code. Okay, that's this program. It's kind of fun, I think. It's useful for checking your code later. And let me see, just real quick. So you got to write these functions first, get those guys working. Some of them are supported by the language, which you can just use the correct expressions in your code. Make sure you're using the logical and not the bitwise. Others you need to generate using some other combination of logic, right? Like implication can be expressed in using and or not. That's one way to do it. You could also use a table. You could do a series of ifs. You could do a switch, whatever. Get these guys working, then use it to test these guys. All right. Okay, have fun with that. Hope this video was useful for you. See you next time. Bye.